Hello and welcome to this very short video on a very interesting bit of research. Now, this research may be simple, but it has the potential to improve the way water is collected in arid areas of the world. Before considering the main research topic of this video, it's necessary to very briefly consider some previous earlier work. Now, earlier work on looking at how water flowed down a single fibre under gravity showed that the preferential drop formation for water down a fibre was something called a clamshell shape. Now, the term clamshell is a term which the researchers use in the more recent work. This earlier work also showed that this so-called clamshell-shaped drop could morph into a barrel-shaped drop. Now, the difference between the clamshell drop and the barrel-shaped drop, apart from their obvious shape, is defined by their contact angle with the fibre. Now, I won't be going into any detail on the contact angle in this video. I will say, however, that for the clamshell-shaped drop, the contact angle is finite, but for the barrel-shaped drop, the contact angle is 0. So on to the current research which I'm discussing in this video. And that work has looked at how water flows down a twisted pair of fibres. And the detail, or most of the detail that was carried out in that research is shown in this first slide. The liquid that the researchers used in this experiment was either silicon oil or deionized water with glycerol added to it. The reason for this is presumably because the fluids are denser than water, makes it easier to film, easier to see as the liquid progresses down the fibre. However, the principles which they derive from their research is equally applicable to water. So on this first slide, there's obviously two diagrams, A and B. The parameters shown on the slide are the thickness of the fibres, that's each individual fibre, not the twisted fibres as a whole, the wavelength of the twists in the fibre, and also the rotational velocity, or if you like, angular velocity. Now, the key ratio in both A and B is the ratio of the thickness of the individual fibre to the wavelength. And in A, as you can see, that ratio gives a value of 0.09. Now, that particular value of the ratio means that, as shown in A, there's a clamshell-shaped drop, and it sort of twists around the fibre. It also has an angular velocity, so what you end up with is this drop that's following a spiral, essentially under gravity, down the twisted pair of fibres. Now, contrast that with the image in B. Now, in B, we're showing the same twisted pair fibre, but there's a different value of ratio. and here it's 0.26. Excuse me. And what you see is that we get a barrel-shaped drop, and this drop wraps around the two fibres completely, the twisted fibres completely, and moves straight down. There's no rotation of the drop. In other words, the angular velocity or rotational velocity is 0. So, as I said, this was a very simple concept. I'm not saying the research was simple. No doubt a lot of effort went into the research, and I'm greatly trivializing the outcomes, but I'm doing that just basically to keep the video short. So the question arises is, what, if there is anything, the usefulness of this research? Well, the usefulness is shown on this next slide. And here we have an image of a bit of coast, and shown on the coast are nets. Now, you can't clearly see the nets. You will if you zoom in on the image. You'll clearly see that there's a hatched pattern in the netting. So in other words, these are nets that are erected on the shoreline, and those nets will capture moisture, water, from mist which is drawn in from the ocean, typically in the early morning. Now that water will run down the net and into some sort of channel at the bottom of the net, and will be collected for later use. Now these nets can also be used inland in arid areas, and the water there will come from moisture which is held in the morning dew. So one of the outcomes of the research, which I've covered in this video, is that the authors of the paper, and there's a link to the paper which I've been discussing in the description below this video. So one of the outcomes of the research was that the scientists propose how to come up with a better design for these nets that capture moisture. Now that topic is what is shown on this slide. So the moisture collection nets currently used in these arid countries and in coastal regions take on well, any number of different forms. They can be simple fishing nets or specifically made nets. However, it seems that most of them are not inefficient in collecting water, but not meeting potentially higher efficiencies for better collection of water. Now, one of the problems with typical netting is that where you have a crossover junction, in other words, where there's a horizontal element and a vertical element, water tends to collect at that junction. Now, this makes the collection process much more inefficient. Now, that is what is shown on the left of this slide. On the right-hand side of this slide is a design which the researchers propose in order to make this netting much more efficient at collecting moisture. So what they are proposing are basically 2 points. The first point is that the droplet that's used should be what they call a clam-shaped drop. And the second point they make is that the clam-shaped drop, which, as we've discussed, will rotate around the twisted fibres. The second point they make is that when it's twisting around the fibre, it should be on the opposite side to the side where a horizontal element is attached to the vertical element, as shown. So with this design, there is no obstruction to the water as it flows down the fibre. There's no pooling at cross junctions, and this makes the collection of moisture or water from the moisture much more efficient. So how do you achieve this? Well, it depends on the type of fibres you're using, and essentially it's going to have to be any design will have to be fine-tuned based on the thickness of the fibre and the wavelength of the twisted pair fibres. But as you've seen, it's not a difficult calculation to carry out, and so I believe without too much effort that moisture collection nets should, without too much difficulty, go through quite an improvement in design to collect more water. So essentially that's the end of the video. Now obviously it's not as involved as some of the subjects I've had in previous videos, but I still think it was worth putting up as a video, and I hope you found it interesting. If you did find it interesting, perhaps you would consider subscribing, and more videos will be coming soon. Anyway, thank you very much for watching.